Welcome back to AI Codecast, everyone. Today we're diving into this pretty fascinating problem. It kind of blends, wordplay with some pretty clever algorithms.
Right.
Um, Counting palindromic substrings.
Yes.
Those words or phrases
Yeah.
that read the same backwards and forwards.
Exactly. Race car or madam.
Yes. And while they might seem like just a fun, linguistic quirk, they actually have real-world applications.
Yeah.
They pop up in fields like bioinformatics, where they're used to analyze DNA sequences.
Oh, wow.
And they can even help optimize certain string algorithms.
So for our listeners who might be new to this, let's break down the problem a little bit.
Sure.
We're given a string, any sequence of characters, and our mission is to figure out how many palindromic substrings exist within it.
Okay.
So for example, the string banana has palindromes like anana, Anna, and even single characters like B, which are palindromes by themselves. That's a great explanation. And here's where it gets interesting. There are many ways to solve this problem, each with its own trade-offs in terms of efficiency and complexity.
Okay, so let's start with the most straightforward approach, the one that might come to mind first.
Yeah.
The brute force method.
Right. With brute force, we're essentially saying, let's check every possible substring and see if it's a palindrome. It's like trying every key on a giant key ring until we find the one that unlocks the door.
So walk me through how we'd actually implement this.
Okay.
No need for actual code, just the general idea.
Yeah. Imagine you have the string banana again.
Yeah.
We'd start by looking at each character individually, B, A, N, and so on. Each of those is a palindrome on its own.
Makes sense. Then we move on to pairs.
Exactly. We check ba and na and so on, comparing the first and last characters. Then we expand to groups of 3. Ban, Anna, Nan, and so forth, always checking if the outer characters match and moving inwards.
Okay, so we're systematically going through all combinations.
Right.
But I can already see where this might get inefficient.
Yeah.
What happens when our string is thousands of characters long? We'd be checking an enormous number of substrings.
You're hitting on a crucial point. Brute force works, but its efficiency drops rapidly as the string length grows.
Yeah.
This is where the concept of time complexity comes in.
Right, time complexity. I remember hearing about that.
Yeah.
It's a way to measure how the runtime of an algorithm scales with the input size.
Right, precisely.
Okay.
In the worst case scenario, brute force for this problem has a time complexity of O of n cubed, where n is the length of the string.
Okay.
This means the time it takes grows cubically with the string length.
Yeah.
Think of it like this.
Okay.
If you have 10 people in a room and want to compare every person to every other person, you end up with about 1,000 comparisons. That's how quickly the number of checks explodes.
Okay, cubic growth sounds pretty scary for large strings. But what about the memory this method uses? Does it gobble up a lot of space as well?
That's where brute force has a silver lining. Its space complexity, which measures extra memory used, is O1.
Okay.
This means it uses a constant amount of memory, no matter how long the string gets.
Gotcha.
We're not creating any large data structures to store information.
So brute force is easy to understand, light on memory,
Yeah.
but it can take forever for long strings.
Yeah.
That leads to the question, are there more efficient ways to do this? Ways that avoid checking every single substring?
Absolutely. And that's where things get really interesting.
Ooh.
There are several clever approaches.
Okay.
And one that stands out is dynamic programming.
Dynamic programming.
Yeah.
I've heard that term thrown around a lot.
Yeah.
It sounds powerful, but also a bit mysterious. What's the core idea behind it?
Dynamic programming is all about breaking down a problem into smaller, overlapping subproblems and storing the results of those subproblems to avoid redundant calculations.
Okay.
It's like baking a cake.
Okay.
If you need sifted flour multiple times, you wouldn't sift it from scratch each time, right? You'd sift once and store it for later use.
Okay, I like the baking analogy.
Yeah.
So how do we apply this sifting flour concept to finding palindromes?
Instead of checking every substring from scratch, we build a table to keep track of whether a substring is a palindrome or not.
Okay.
We start with all the single characters, which are always palindromes.
Right.
Then we move to substrings of length 2, then 3, and so on.
So we're building up this table piece by piece.
Yes.
But how do we actually fill it in? There must be some logic to determine if a longer substring is a palindrome based on the shorter ones we've already checked.
Exactly. Here's the key. A substring is a palindrome only if its first and last characters are the same.
Yeah.
And the substring between those characters is also a palindrome.
I see. So when we're checking a substring of length 5, for example, we can look back at our table to see if the inner 3-character substring is already marked as a palindrome.
Exactly.
That's brilliant.
Right.
We're essentially reusing our previous work.
Precisely. And this clever reuse of information is what makes dynamic programming so efficient. It avoids unnecessary repetition.
This is making a lot of sense.
Yeah.
Now, I'm really curious about how much this table approach improves our time and space complexity compared to the brute force method.
That's a great question, and we'll dive into that comparison in detail
Awesome.
right after a short break.
Sounds good. We'll be back in a moment to unpack the efficiency of dynamic programming. Welcome back to AI Codecast. Before the break, we were talking about how dynamic programming tackles this palindromic substring problem by building a table to store results. It sounded a lot more efficient than brute force, but how much better is it, really?
That's the exciting part. By using this table and reusing results, we bring the time complexity down to O of n squared.
Okay.
It's still quadratic, meaning the time grows with the square of the string length, but it's a major improvement over the cubic growth of brute force.
Okay, quadratic is better than cubic, I get that. But to be honest, big O notation still feels a bit abstract to me sometimes. Can you give me a real-world sense of what that improvement means?
Absolutely. Imagine you're organizing a party and need to arrange seating for everyone.
Okay.
With brute force, it'd be like comparing each guest to every other guest individually to figure out who should sit where.
Yeah.
That would take forever with a large party.
Right.
Dynamic programming is like having a seating chart where you can quickly see who's compatible with whom based on their interests, making the process much smoother.
That makes so much more sense.
Yeah.
So we're saving a lot of time with dynamic programming.
Yeah.
But what about memory usage? Doesn't that table take up a lot of space, especially for long strings?
You're right to be thinking about space complexity. That table does have O of n squared space complexity, meaning the memory it uses grows quadratically with the string length. But here's where dynamic programming's flexibility shines.
Okay.
Often we can optimize that space usage without sacrificing the time efficiency gains.
Wait, we can make it use less memory. That sounds almost like magic. How do we do that?
It's not magic, just clever observation. The key is realizing that we don't actually need to store the entire table to calculate our results.
Gotcha.
Think back to how we build it.
Yeah.
We start with single characters, then pair, then triplets, and so on.
Right. So each row in the table represents substrings of a specific length.
Exactly. And to figure out if a substring of, say, length 5 is a palindrome, we only need the results from the row for substrings of length 4.
Okay.
We don't care about the results for even shorter substrings anymore.
So we're saying we only need to keep track of the previous row while we're calculating the current one. Right. Couldn't we just overwrite the old data?
You got it. We can drastically reduce memory usage by simply overwriting the previous row with the new calculations as we go. This brings the space complexity down to O of 2n, which is essentially O of n.
Wow, from quadratic to linear space complexity. That's a huge improvement.
Yeah.
It's like decluttering a messy room and realizing you only really need a few essential items.
That's a great analogy. But it gets even better. We can actually optimize this even further and achieve the same results using just one row.
Hold on. A single row. How is that even possible? It seems like we'd be overwriting data we still need.
It requires some clever indexing and careful bookkeeping.
Okay.
But it's totally doable. The basic idea is to iterate through that single row, updating each entry based on the previous ones in the same row.
Yeah.
The trick is to do it in a specific order
to
avoid overwriting information prematurely.
I think I'm starting to get the concept, but I imagine the actual implementation can get pretty tricky.
It definitely takes a bit more thought, but the reward is significant. We get all the benefits of dynamic programming, the efficiency, the organized approach, while using minimal memory.
This is incredible. It feels like we've unlocked a secret level of optimization. We've taken an already efficient algorithm and made it even more powerful by being smart about memory management.
Exactly.
Yeah.
And this principle of reusing and overwriting information can be applied to many dynamic programming problems.
So
it's all about analyzing what data is truly essential at each step.
So dynamic programming is clearly a game changer for solving the palindromic substring problem.
Yes.
But you mentioned earlier that there are even more ways to approach this. What else is out there?
There are indeed other methods,
Okay.
some even more efficient in certain scenarios. One is the expand around center approach,
Okay.
which cleverly leverages the symmetrical nature of palindromes.
Expand around center. That name definitely sparks my curiosity.
Uh-huh.
Can you tell me more about how that one works?
Sure. We'll explore the expand around center approach in detail right after we take a quick break. Stay tuned.
Welcome back to AI Codecast. We've been on quite a journey exploring ways to count palindromic substrings. We started with brute force, then leveled up to dynamic programming with some clever space optimization tricks. Now, you mentioned an expand around center approach. What's that all about?
So this method takes advantage of a key property of palindromes,
Okay.
their symmetry. Instead of building a table like in dynamic programming,
Right.
we focus on each character in the string as a potential center of a palindrome.
Okay, so instead of looking at substrings directly, we're thinking about potential palindromes growing outwards from each character.
Exactly.
I like the visual of that. How does it actually work?
Imagine we have the string race car.
Okay.
We start at the first character R
Uh-huh.
and treat it as the center of a potential palindrome.
Right.
We expand outwards, checking if the characters to the left and right match.
Yeah.
In this case, they don't.
Okay.
So the longest palindrome center to R is just R itself.
Then what? We move to the next character.
Exactly. We move to A and repeat the process. Okay.
We expand left and right,
Uh-huh.
and in this case, we find a match. Aki. We keep expanding outwards,
Yeah.
but R and E don't match, so Aka is the longest palindrome centered at A.
So we're essentially radiating outwards from each character,
Yep.
looking for symmetrical matches.
Right.
It feels more intuitive than building a table.
Yeah.
What about those palindromes with an even number of characters, like Abba?
Great question. For those, we treat the space between two characters as the center.
Oh.
So in ABBA, we'd expand around the space between the two B's.
Clever. I see how that covers both even and odd-length palindromes. What about the efficiency of this method? How does it compare to dynamic programming?
Expand around center actually has the same time complexity as dynamic programming, O n squared. We might end up checking some character combinations multiple times,
Okay.
especially for longer palindromes. However, it has a major advantage in terms of space complexity.
Yeah, let me guess. It's more memory efficient.
Yeah.
Because we're not building a table. Exactly. We're only keeping track of a few variables as we iterate through the string, so the space complexity is O1, just like brute force.
So it's a trade-off. Dynamic programming is great for avoiding redundant calculations.
Right.
But expand around center wins in the memory department. It's like choosing between a powerful computer with lots of RAM and a sleek, portable laptop. Both have their strengths, depending on the task at hand.
I like the way you're thinking about these trade-offs. And it's important to remember that the best approach often depends on the specific constraints of your situation.
Right.
If you're dealing with limited memory, expand around center might be the way to go.
This has been an amazing deep dive into the world of palindromic substrings. We've learned about brute force, dynamic programming, expand around center.
Yeah.
And it's amazing how a problem like this can have so many different solutions, each with its own strengths and weaknesses.
It is.
I feel like I've leveled up my understanding of algorithms and problem solving just in general.
I'm glad to hear that.
Thanks for joining us on this coding adventure, listeners. We hope you've enjoyed learning about palindromes as much as we have. And remember, the next time you're faced with a tricky coding challenge, take a moment to explore different approaches. You never know what clever solutions you might discover.
Until next time, happy coding, everyone.